the power plant is going up and down like this. So it's a bit different how these power plants are operated. But so when the frequency go down, which is caused by that you are using the inertia in the system, then you start to react. And the question is how fast you start to react. Do you react after 1 second or 2 seconds or after 3 seconds? Because this is important in the future when you have lower inertia in the system. If you get a faster, if you have low inertia in the system, perhaps you can have a faster primary control. Then the frequency will not drop so fast. Because nowadays it's normally that the primary control of today is designed based on the requirements we have today and based on the amount of inertia we have today. This is very much discussed today because the question is, do we need more inertia or do we need a faster primary control? You can have one of these solutions because you challenge if you, let's say we have 80-90% of the production from solar and wind power, then you are significantly reducing the amount of inertia in the system. And then, of course, and then the question, do I need more inertia? No, I need faster primary control. The problem is that is, of course, affect the whole system. If you just go back to these guys, you tell these guys that if the bike goes slower, can you please bike a bit more? But the problem is that then you have to tell all these guys that if the bike goes a little slower, you have to be much faster because our bike is now, if everyone is only have a 1 kilo weight here, and the bike is so plastic, and then of course they have to act much faster because when someone is biking faster, the bike goes fast, and if someone is braking, it goes down directly. So you have to be much faster reaction. But then you have to tell them, of course, and they have to react on that. And that is, of course, a challenge in the power system. Let's say, take India, for example. I mean, just tell every coal power plant in India, oh, you have to react faster. You have to change your control system. And it may be also like this, that you should have one setting at high wind and high solar penetration, and then in the night you should have another setting because then you have a huge amount of synchronous machines. So that is, of course, a challenge here that you have to have someone that is reacting, but on and the question is how fast they react, maybe depending on the state of the system. Very interesting control science issues. So what is happening here is that the frequency go down, and then hydropower plants say that, okay, I should produce more. Okay, I should produce more. Okay, I should produce more. But it takes a while. And then the frequency now is stable. So now we have a constant speed. So now, but then here, the hydropower plants thought that they should produce more. So they still start to produce more. And because of that, the frequency goes up. And then you can, of course, formulate this as differential equations. Then you get the swing equations and so on. So there are, let's say, oscillations here depending on, let's say, the delays. If they were faster in the primary control, you get less of these ones. And then I think that what I know is that in Sweden we have the hydro system, and hydro is from this point a bit slower. You have a so-called minimum phase reaction, which means that they are rather slow in the reaction, while so in Sweden we also keep a rather wide band of the frequency because it's difficult to react on milliseconds. Why, if you have thermal power plants as coal or nuclear or these, they can react much faster. So they, for example, in both United States and in Central Europe, you have plus minus 0.01 hertz, plus minus 0.01. Here I understand you have plus minus 2 hertz or something like this. It's the same as, you have the same as United Kingdom in reality, what they have currently at least. Here you see a difference. These are frequency drop after 3 real outages in Sweden. Then you have something called the rock-off, which is very much discussed nowadays. Rate of change of frequency. The rock-off is in reality how fast will it. It's the same thing that the rock-off, if you have this bike with guys and someone is braking and it's 1.3 ton, then the bike will slow down rather slowly. On the other hand, if it's 1 kilo guys and the plastic bag and they suddenly brake, then it stops directly. And that is, in reality, in the power system, it corresponds to this rock-off, rate of change of frequency, which depends in reality on the inertia in the system. And that what you see here is that the rate of change of frequency in Sweden is rather different. It's very easy if you know the power system, when it's big and when it's small. Because in the summer, in Sweden, we have very much load. Because we have very much, the winter demand is like this, the summer demand is like this. So in the summer, of course, there will be less synchronous. So it's less inertia in summer compared to the winter. So inertia here, and that is exactly what you can see here. That here, this is the black one that is dropping here. So that is here in June when we have the low load. And then we have the blue one, which is in the end of November when we have a much higher load. And when we have higher load, then we also have more synchronous machines, so then this is not a problem. So, and then the question is, assume that we in June, in this case, had 80% of the production from wind power, where you don't have a direct connected synchronous machine. What will happen with the frequency? And these are the type of problems we are currently discussing very much in Sweden. And so, and we have had in Sweden, it was very interesting. We have had from the political point of view, we have had a discussion of the future energy policy in Sweden. And then we have, of course, discussed possibilities of renewables and this kind of thing. But then a lot of engineers have brought up this issue of inertia. What was interesting is that there were a lot of politicians that started to talk about, yeah, the inertia is important, and the reactive power is so important. So, and it's a lot of them, they really understood what they were talking about. Not everyone, I can say. But I mean, it was so suddenly, because this is one of the fundamental issues, that how do you manage the mainly the inertia. But now what is happening is that probably since we will get I heard now that there came a new report, so now the politicians have to learn rotor angle stability, which is the next challenge. Anyhow. So this is, here you see that the inertia is in reality. So we have, for example, PhD projects now to identify the current inertia in the system. I mean, because the problem is that which power plants are online, of course, do you really have measurements of all this? And so this is very, I can tell you about the Irish problem is something. Because it's not only wind and solar power, it's also HVDC. You have the same challenge with HVDC. We take Ireland here, and then they have here HVDC to Scotland, and then they have another, I think this is 400 megawatt, and here they have, I think it's 600 megawatt, and it's also HVDC. To Wales here, and then they have a huge amount of wind power, and then we have Northern Ireland here, but it's a synchronous system. The problem they are discussing is the following. Assume that we have a huge amount of wind power, and we are importing on this HVDC line, and then suddenly you get a problem there. Then you can lose 600 megawatt. What does then happen with the inertia in the system? Because you don't get any inertia from these ones. Yeah, it's a bit lighter perhaps somewhere. Ah, that's better. So this is the issue. And what is important with HVDC is that the fundamental issue of inertia is synchronous machines. HVDC never provides any, it's not a synchronous machine. Let's say you have the following. We take away these ones, and we start to build a line which they are discussing down to France. And here you, to France, they are discussing that. But assume that you have a situation like this, where you have every import on synchronous machines, and then suddenly you lose this one. What happens with the frequency? You don't have inertia in the trading from the HVDC, but there is. I know that ABB has a patent on that. You can, of course, measure the frequency here, and then more or less instantly you increase the production, you increase the transmission on this one, based on that you are not already running on the maximum here. So you can get so-called synthetic inertia through this one. Synthetic inertia, I can say that synthetic inertia, it has been discussed that this is probably the wrong word. Synthetic inertia, if you go back to the fundamental issue here, and that is this one. What I said here is that the power go down, and then instantly you get the power, and that is how it works in a synchronous machine. Instantly you get exactly the amount of power there. Then the frequency starts to decrease. Synthetic inertia, which is very much discussed, and they claim that they have it in wind power on this, it's normally based on frequency measurements. This means that it's not a synthetic inertia, it's more a fast primary control, because then, of course, the frequency has to decrease a little before you get extra more power. Here, you have an instant. You didn't, I mean, this you got instantly. You didn't first have the frequency decrease. You first have the inertia response, and then you got the frequency decrease. It was not the opposite, which you have in the synthetic inertia, that you first have to get the frequency decrease before you can get to the inertia. So the question is really how this is working in reality. So I don't think synthetic inertia is really the correct word. It's more an extremely fast primary control. So the question is little, and that is very much the challenge here, that let's say you have this bike with guys. We take them up again. Assume that these guys, the weight of them is 1 gram. And then, no, I mean, the problem is that if someone breaks, and then you tell them, can you please start to increase if the bike goes down? The problem is that you brake, and then it stops more or less immediately, the bike, if someone is braking. And then, of course, can you please bike a bit faster if the speed drops? Yeah, but it stops directly, the bike. Sorry. So I can't bike because it has fallen, because it was not running any longer. So I think that if you have very low inertia in the system, this synthetic inertia is more some kind of extremely fast primary control. So this is really one of the. On the other hand, as I said, for example, for Sweden, I don't think this is a very big issue, because you are also you always have to run some hydropower plants. You have the industrial back pressure units. But I mean, in some way, this has to be solved. So, I mean, let's say you come to, let's say 30% solar power in India, for example. Then there may be situations when you have very huge amount in the middle of the day, when you have nearly all the production perhaps coming from solar power. And then the question is, but how do you handle the inertia if you get some problems in the system? And you have another issue with just here also. What you do here, which is important, is that you have the inertia, and then you got the frequency, and then you increase the production. That is what I said here. Okay? You measure the frequency here, and then you control the power that is going into this power plant. But then, of course, there must be a margin here. So you cannot run a power plant that is participating. This cannot run on its maximum. So you have to have some kind of margins in the power plants. And that is, of course, an issue, because all solar and wind, of course, you want to run them on maximum, because that's, I mean, it's cheap power. It doesn't cost you anything to run them. So, of course, every solar and wind power plant will produce as much as possible. Well, why should they keep a margin? But it's technically possible. There have been a lot of tests. I know there is a offshore wind farm in Denmark called Horns Rev, and they have implemented frequency control in the wind farm. So they are keeping down, and this is very much to keep margins in plants. It's very common nowadays. In solar power, I have not heard anything that technically it's of course possible. You have a converters, you can decide how much you should produce. But in reality, I have not heard so much that they are trying to keep margins in solar power. You could have it in isolated systems, of course. Okay, so you first have, and that is the balancing in the different steps. You have the inertia, and then you have the primary control. And it goes up to minutes, but it's also it starts within some seconds, but then it depends on how long this frequency drop is. Inertia in seconds, it should be in reality smaller than seconds. Okay, so the inertia, you have it in other power plants. Technically possible in wind power plants. This slide is not written, to be honest, yesterday. I should try to reformulate it a bit, because there have been more discussions exactly on this issue, and we are discussing one in this area. I will say just a little about the so-called synthetic inertia, because this has very much to do with a converter design. For example, if you apply, and it also has to do with faults, the fault currents also has to be high, and that is also a challenge, because today you have a fault current, and it also comes from the synchronous machines. If you suddenly get a fault here, you directly get the current from this one, and the faults are the fault currents are in order to identify that we have to. And if you the problem is that if you take away the synchronous machine, how can you get any fault currents? That is another issue. I will not take up that. An interesting issue. Just about wind power, we have this so-called synthetic inertia, which is, to be honest, I don't think it's really correct. Here, you have a wind power plant. You may have a gearbox here. And then you have a generator. Here you have a generator. And then you, in the type 4, what you normally have today is that you here have a AC, DC, AC in some way, and then you have out here. Let's say that this is a 2 megawatt unit. So you are suddenly producing 2 megawatt here. And you are suddenly sending out, we take it lower just to say something, 1.5. And then you are sending out here, we neglect the losses, 1.5 megawatt. Okay? Of course, this will rotate with the same speed. Assume now that we so-called synthetic inertia, or I think call it fast primary control, which I think is better, because exactly inertia instantly, and the frequency is not dropping. I mean, you have to have synchronous machines or some kind of inertia in order to make the frequency really drop. Of course you have it, because very much of the demand today, if you take a fridge, for example, it's a motor. In the motor, you have some synthetic. So even if you only have the production side, also in the consumption side, you have some inertia. For example, I think these ones, no, the question is these ones, are they, I think it's a direct motor, but I'm not sure. It may be power electronics, and then you don't have any inertia. It's probably power electronics. Pardon? Single phase. Yeah, but still it's a machine, so it's inertia in it. But how do you control the speed? Is it power electronics? Okay. Okay. Because I mean, what I mean is that in general, in the industry, for example, you have a lot of motors, and the motors are nowadays. What is happening? The interesting thing is that the inertia in the industry has traditionally been, because you have had a that have often been asynchronous machines, induction machines that are connected directly to the grid. And this means that there is less inertia, but at least some inertia in these machines. What is happening nowadays, you want to save energy, you want to have a controllability of the speed of the motors, so you are putting in power electronics in between the grid and the motors. And then, of course, you take away all these kind of inertia also from the load side. But you still have some of them, I'm sure. Anyhow, what you do here is that what you can decide here, since this is a converter, what you normally do in the converter is that you see that, you check the speed here, okay, it's 1.5 megawatt, and then you decide that, okay, I send out 1.5 megawatt here. Here, this is completely controllable. You have a specific P here that you can send out, and what we also have discussed is that it's a specific Q that you can send out if you want. It's totally controllable, this one. So what you can do is, of course, to measure here the frequency, and then you tell this one 1.6. What happens? Then this one will speed down. But it's exactly the same thing as in the conventional one, because here you have a real inertia in wind power. In solar power, you don't have it. So there you don't have this possibility. But in wind, you have inertia, of course, because you have a big thing that is rotating here. The interesting thing is that here, the inertia here is a physical thing. So you have a specific H value of this one, where you have a specific mass that is rotating, so you know the inertia in this one. Here, you can control it completely. On the other hand, it depends, then of course this one will speed down. And what is happening when it's speeding down, what you normally try to do is then you have the pitch angles on the wind power plants like this, you can pitch them. So what you normally try to do is to keep an aerodynamic efficiency. If this one speeds down, you will probably not get as much energy from it, so you are also decreasing the production. But at least, so you want to have a specific speed which is optimal of this one, the rotational speed, which is optimal for that specific wind. But of course here you can decide. Now I said that, okay, the frequency one produce 1.6, and no, produce 1.7. Whatever. So you can have this is a so-called P controller, so you can control this one if you want, and that is implemented. For example, it's synthetic inertia, it's called, and in Canada, for example, they have implemented in their wind power, which I think is extremely strange, but it became I think it depends on that they are French and they like technology, because I mean, because it's in Canada, in eastern part of Canada, where they have 100% hydropower. I don't understand at all why they need inertia in a power system where they have nearly 100%. I mean, they have a huge amount of hydropower. I think it's more than the Nordic system. And then they start to have synthetic inertia in a very few wind power stations. But of course, it's very good that they have it, then they can test it. But they need it, I don't think. But it's interesting technology. Anyhow. This is the synthetic inertia, because you have an inertia. I mean, synthetic inertia is not really the right word, because here you have a physical inertia. You have a big thing that is moving around, a lot of tons or kilos that is rotating. So of course you have an inertia here, and this means that technically that's not a problem to have mechanical power of 1.5 megawatt that is coming in here as the wind, and then you are taking out 1.7 megawatt in the other end, and that means that this one will speed down. But then, of course, there is a limit. You can only let it speed down to a certain level, but that is the same thing with this one. You cannot allow it to speed down too much. So here, the issue here is of course, how should you design this? Should you I mean, sometimes it's windy there, sometimes it's windy there, and then the question is, always have the same of this one. They say, this is fantastic PhD projects. How should you in reality set these synthetic inertia parameters in a power system where the wind is varying up and down like this? Can you always tell them to have the same relation, or how should you handle that? Because now everything is controllable. The problem, the benefit of controllability is that you have the fantastic possibility to do whatever you want. On the other hand, the drawback is that you have to do something. You have to think about what you should do. If you come with a synchronous machine, okay, you will get an inertia. It's not controllable at all. You just know that this is what I get. I have to consider it. So that is very much discussed nowadays. So one way of doing it, and that is very much, you can call it a traditional idea from what I see, at least the system operators, is that they say that we know this. Can you please try to behave in the same way? On the other hand, the question is that, but why? We can perhaps do it much better. We can be much faster. Why should we do it in that way? Know how this works. The problem is that I completely understand the issue, but it's of course an issue that it may happen that in the future we can get a much better system, much more stable frequency if we just handle this in a good way. So there are fantastic possibilities here to really get a good thing out of this. So that was a technical possibility in wind power plants, which I don't think is really correct. There is a discussion, because in here, as I said, I'm not really an expert, but I think that, let's say you have a converter. The question is, if you have a converter, let's say you have this is interesting. Let's say you have a DC voltage here, which is kept constant. We say that it is constant. And then you have a converter here, DC, AC. Let's say it's an HVDC, for example, or you have a battery storage here or something. And here you're sending out 1.5 megawatt to a house here. And suddenly they say that, no, I want to have 1.6 megawatt. I think this is technically possible to do that, which means that instantly, when they change from 1.5 to 1.6, you get 1.6 here. I think that's physically possible. That's the way it works. What is that? That is synthetic inertia. So that is not based on frequency. Remember that. The question is how that works, and how this works if you put this together with a lot of synchronous machines and wind power plants. One PhD project more there. Okay, so this is of course an interesting challenge, because we are discussing exactly this kind of fundamental issues. Of course, this one must have the capacity of delivering 1.6 megawatt. Otherwise, what is happening is that you don't have the problem in the converter is that you have these ones you can open. If you have a 1,000 megawatt turbine, you can during a second or 2 or 3 or 4, no problem to get 10% more. It's a mechanical issue. You can, if this is a turbine, then let's say that this is a HVDC, and this is dimensioned for, let's say, 1.5 megawatt. What happens if you try to get out more is that, no, you get the current limit, like this. You get it instantly on the millisecond, because you have controllers for each transistor that is controlling this one. So you have, because otherwise if you during, I think the sensitivity is that if you during 10 milliseconds or less, you try to overload your converter, you burn the transistors directly. So you can never, that is also a discussion nowadays in the other PhD project. How can you have some kind of cooling in the transistors, or have some kind of more metal connecting to them, so you can overload them for a short while, because that is extremely attractive nowadays, that you perhaps can have an HVDC, but you could contribute with inertia, so you have an overproduction during, let's say, 1 second or something. So that is also a discussion that is going on right now. Can you rechange your power electronics so you can overload it? I never talk about what I'm reading. Okay. Okay, so today we have the contribution of this inertia. It's from hydropower station, use synchronous machines, and you have the same with coal power or all these thermal power. So it's rather easy. So you get the inertia. It's not a big problem right now, not in the Nordic system, but they are discussing it, because if you don't have it, the power system will not work. And in Ireland, it has been like this, that they have said that we do not allow more than 50% of the instant power coming from wind power, because we may have inertia problems. But now I heard that, but then they have said that we have to check these rock-off things, the rate of change of frequency, because they have out in their systems, they have rock-off sensitive they have rock-off relays that are checking that if the frequency drop too fast, they can disconnect some areas. And then it may happen that they are disconnecting an area where they have a huge amount of wind power. So if suddenly you get a problem, you see the frequency drop, then you disconnect production, and then you make it even worse. So what they have done in Ireland is that they are checking the relay system and checking how this is looked like. But now I heard that they have allowed, so they are discussing 50% wind power. Now they are perhaps speeding it up to perhaps 60%. I think they have said that they probably can get up to 75% instantly. But that is an extremely system, and it has very much to do with that they dominating fault. I think I wrote this is Ireland. Sometimes they have this is an extremely small system. I think that sometimes the demand is, let's say, 3,000 megawatt. And then, of course, if they have an import of 600, functioning fault is extreme. If you have 30 guys on the bike and suddenly 6 of them stop biking at the same time. I mean, in India, for example, the dimensioning fault is extremely much smaller in percent. And the reason is that if you have such a small system where the dimensioning fault is, in this case, it's, what is it, 20%. 20% of the capacity is in one unit. I don't think that 20% of Indian consumption can be in one unit that you can lose. Of course not. Then you can lose transmission and so on. But when you have such a small system with large units that you can lose, then of course inertia can be a big problem, because here you lose a very big part. In India, I don't think, because India is such an extremely big system. If you lose one unit, it's not a big issue. But so that's why they are limiting, I think, the wind power to 70%. If you have a bigger system, the dimensioning fault is not that big, so then of course you can manage it with lower inertias. You can accept more solar and wind power. The challenges. One of the challenges is more slimmed construction may reduce the inertia. That is discussed in Sweden, that when you build new units, of course, to buy this is very heavy, big like this, and if you take a power plant that was built in the 1960s or 1970s, they were over-dimensioned, big, thick things like this. But now you're optimizing the construction, so perhaps, we can do it slightly smaller. We have aluminium instead of steel or whatever. So then they become lighter. This has been a discussion. And then you get automatically less inertia. And then you have, of course, all this HVDC. You have also the demand that is decreasing. They have more power. So the more power electronics is fantastic from the power system point of view, but it's reducing the inertia, which is the fundamental issue here. So it's not only the wind and the solar power, but I mean, wind and solar is, let's say, the large contributors of the change. This is what I talked about earlier. And that was the challenges. You should solve C2 and C3. That is what I said. Low wind and solar power production at high power consumption. This is the challenge, and I think with a huge amount of solar power in India, I think the night will be the more challenging part, because solar power will probably normally match the peak in the day. I don't know if perhaps you have a peak at 5 o'clock or 6 o'clock in the evening. And then, of course, if the solar power go down, I have not seen any graphs, you can probably draw it very easy. If you have the total demand of India, and then you see, let's say, if you have let's say 30% of yearly energy from solar power, where will you get the peak instead? And then the question is that at these situations, you have to have enough capacity. And then what I say that if you solve this, and then of course you also have to solve this kind of situation, you have to have enough controllability to manage perhaps synthetic inertia, or perhaps gas turbines where you disconnect the rotor from the machine or something. You have to solve the problem of inertia. And if you have this solution, and if you have this solution, then you should start to think about, will I get problems up here? Because then you have all these kind of units that are controllable and could contribute to different kind of things. For example, in Sweden, we are running sometimes hydropower in air, just because then you could just put on water and start to produce. So they are rotating in air. Okay, they are creating some losses, but they are in reality working as a synchronous machine, which provides inertia and all this kind of thing, and also the reactive power. And then they of course can act as fast reserve, and then if you put on water, you can also produce more power, and then you can handle the continuous balance. This is the way I think, because people, as I said earlier, sometimes are only focusing on this inertia issue, and then they say, inertia will be a big problem. Yes, it is, but then I tell them, but okay, which resources will you have? Don't you have some kind of gas turbines that you perhaps could run anyhow? It's just that you have to purchase the type that you are disconnecting these ones from each other. Okay, this is the synchronous machine. Wind power plants do not normally contribute to keep reserves. I mean, the wind power plant works like this, that you have the wind speed here. Normally they start at around 3, 4, 5 meters per second. Then it's enough energy in the wind to make it rotate. And then you increase the power production like this. And then you normally have something called a rated wind speed, which is sometimes between 11 to 15, something like this. And then you normally twist the blades, feathering the blades like this, and then you decrease the production up to this level, and then at extremely high winds you disconnect them. So this is the basic behavior of wind power. So here, and that is a bit important, it's in this region where the wind speed is varying a lot. Because it's important to remember that when it's not so windy, you don't, of course, get any extra variation from wind. When it's very windy, you don't get so much variation from wind speed either. So the issue is then when you have not the installed capacity of wind power. Sometimes I say, so it's important, let's say you're in a country, let's say we have, I don't know how much, let's say we have 10,000 megawatt wind power, just as an example. First of all, how often do you get 10,000 megawatt? Never. Of course. And that is a big difference. If you have 10,000 megawatt of coal power, you can get 10,000 megawatt. 10,000 megawatt of wind power, you never get 10,000 megawatt. Because this means that 10,000 megawatt of wind power, let's say just we make it simple, it's 2 megawatt units. 2 megawatt units. This means 5,000 units. 10,000 megawatt means that all these 5,000 units should work at the same time. They should be available, and that all these wind turbines, the wind speed should at the same time be between 15 meters per second and 25. How often happens that? Never. So the question is always, when you have 10,000 megawatt of wind power, how much do you get? Never 10,000 megawatt. Maybe 9,000. And that depends on the availability and how close they are. If they are very much spread out, how often is it really windy everywhere at the same time? So that is, let's say, step one when we talk about wind power. This is about control. So here they cause. So in so when it's very low, they do not cause so much requirement of wind power. And then on the other hand, when it's up, when it's very high wind, when they're close to 9,000, you don't cause so much extra. It's here in this region where you get the changes. And then the question is, do they contribute? That is technically possible. You can, of course, tell this wind power plant, don't run on this level. This, let's say this is a 3 megawatt unit. Don't produce there. Produce there. This is not totally correct either. Now I see what I wrote there. Because let's say you have a surplus in the system. Then, of course, you can tell this one, please decrease. So let's say you suddenly get a surplus in the system. Then, of course, this one can have a frequency control that if the frequency go up, they should decrease. That you can easily implement. But then, of course, if you decrease the production here, the wind power owner don't like that because they want to produce on the maximum all the time. So it's technically possible to have a frequency sensitivity here. So if the frequency go down in the system, if the frequency go up in the system, you should decrease your production. That is technically possible, of course. It's the same in solar power, of course. To be honest, frequency control, primary control, is absolutely not a big issue when we talk about wind power. Just the reason is that if you go in and look on time series of wind power, or realistic time series, they are varying rather slow in reality. It's not, the rapid changes, the frequency control is, as the primary control is what is happening within, let's say, 5 minutes or something. Then you have the primary control that has to react. But you can have, of course, changes. Let's say you have 10,000 megawatt wind power, so this means that, let's say, the maximum may be 9,000. Then you, of course, can have one situation when you get, let's say, 1,000, and then it's an increasing trend like this, and then after a while you get 9,000. But this time here is hours if you only have this. Because, you'd never see that suddenly you go from 0 up to something extreme, and then, of course, it can decrease from 9,000, and then it can in some way decrease down to, let's say, 1,000 here, minus 8,000 megawatt. But this is, we talk about hours here. You don't see that the wind, because remember that 5,000 units, you don't have them in one point. So even if the wind can decrease very fast in one point, yes, but sorry, 5,000 units, they are spread over a rather large area. So, of course, the wind speed is not decreasing very much on all these points at the same time. So primary control, the calculations as that have been, they are causing some changes in the system, but it's not so much the primary control that is affected. It's mainly the slower things that you can get large changes within hours. Remember that the figure I showed you earlier, and then you saw that, oh, the wind power is decreasing. But if you looked on the time scale, and that was measurements from Sweden, if you looked on the time scale, it took hours to go from the maximum, or nearly days to go from the maximum down to nearly 0. So this is not a primary control issue. It's more, on the other hand, it's more, let's say, several hours. That can happen a lot. But then, of course, primary control must work, and then, of course, primary control is connected to inertia, which is also, the inertia is a challenge. Oh, sorry. Yes, just, I don't know how, we'll see how much I will talk about all these details here. Just a little about, to understand the next step. What is happening when you have used the primary control is that you have another frequency, lägre, it's lower. And then what have happened is that you have some kind of primary control units here. They are increasing their production. So now you have a balance in the system. It's important to remember that primary control doesn't solve any problem. It solves the inertia problem. You have the inertia, which is the physical reaction. Then you have the primary control that is stabilizing the system. Remember, it's stabilizing the system. It's stabilizing the problem. It's not solving the problem. Because what is happening now is two things. Here, you had some margins, primary control margins. Then you got the problem, and then you use the margins. So, of course, now you don't have so much margins any longer. This is the problem, of course. You get the problem in the system. And you have solved the problem initially, but now you don't have so much margins. The question is, what happens if I get a new problem now? Then I increase more. Do I have more margins? I don't know. So I have used my margins, and I don't have the right frequency. So if I get a new problem now, it can be severe. So then you have the secondary control, which is the next step, which is sometimes also used to release the lines and so on. So then, of course, you have to start some units, but that you can do a bit later. Here is the initial automatic system, and here you have to start some other units, which is the secondary control. And that is a bit longer time, and then, of course, you can have more changes in wind power during the time and so on. So the secondary control is the next step, adjust the frequency. And the power system should be ready for a new load or wind change or something. And the power system should be ready for a new system. And then you have this also the AGC. Because, let's say, what is happening in reality, and this is... Is this in India? Nearly. Okay. We have a lot of transmission here. Let's say here we have a coal power plant here. And suddenly this one changes. You lost it. And then, of course, have the inertia. And the contribution comes from all over India because we have a synchronous system. And then you have the primary control, which is probably also spread out in some way. Then you get the change here, change here, change here, change here, change here. Now, if I make it there happen so many things at the same time in a large country as India, but just to make it extremely simple, if you do something here, it will have an impact on the transmission also. And then that's why you have this so-called AGC, where they are checking that, there I have the. Let's say that we have an area here. And then if you suddenly lost this one, then what is happening is that then you get a change in the flows towards this region from the other regions in India. And then, of course, so you and then I don't know exactly how this is set up in India, but a very common rule is that you do that. You got a problem in your region. You have to fix that in your region. So that means that you have other power plants here, and they should increase. So here first you got minus 600 megawatt, and instantly you have the primary control, the inertia that, and then in reality, after a while, you can say that you have to add plus 600 megawatt, and that you can easily identify area exactly what is happening. I assume this is called control areas. I assume that, does anyone know? I assume set up that this is the setup in Europe and in US, for example, that you do it in this way. And this is, the issue is, I'm not so sure that this is really how you should handle the system. It may happen that, let's say this is not a power plant. Here you need local balancing all the time. So in this area, but that depends on the size of the system. What they are doing in the United States, for example, is that originally they had very small control areas like this. And this means that if something happens there, for example, the wind is going down and the wind is going down, or the solar is changing, or outage in the coal power plant, then they are measuring, and then they say that, aha, you have a problem, you have to fix it. You have a problem, you have to fix it. You have a problem, you have to fix it. What they are instead doing is that they start to coordinate over larger areas and say that, okay, yes, we got a problem here. Yeah, but the cheapest way was to, in reality, to compensate it there and there. So why not continue with that? And this is, of course, a smart way of doing it. I mean, you should, instead of having this a bit, you can call it conservative in United States. To be honest, I know that they are very conservative on the west side, especially up towards Canada. They are a bit more conservative. So I heard that they have extremely big problems in doing this, because wind, they say that, no, I have very big problems with my wind in my area because I have to compensate it here. And then they have hydro in the next area. But sorry, why don't you compensate it there? No, we have rules for how to trade between the areas. So if something is happening here, I have to compensate it here. And my plans are very bad. But sorry, why do you do it? No, we have our rules. And that is the problem, that it's very problematic. I'm so surprised sometimes when I talk to power system engineers, why they don't go back to the basics. The basics is that we should run it efficiently and we should consider physical limits. But then they say, no, we have rules. But are these rules efficient? Yes, maybe if you have coal everywhere. But if you don't have coal and you have transmission, perhaps do it in a smarter way. I don't know anything about India, how this is handled in India, but I think it's certainly one of the bigger issues, this with AGC, how to handle. So that on the other hand, if you take more eastern part of the United States, you have Pacific Gas and the PJM area. There they are, in reality, they are thinking more, what is rational? What should we do? How should we handle this? Which is, of course, very interesting. Then you get more interesting, let's say, solutions and think about what is really good. In the Nordic system, to say something about that, we are, of course, very rational, since I come from the Nordic region. And, in the Nordic region, it works like this, that we have Sweden, then we have Finland, and then we have Norway, and then we have Denmark here. It's two Denmarks. We have Eastern Denmark, and then we have Western Denmark, and they have a DC line here in between. We don't even have a secondary control. We don't have control areas at all in Sweden, in the Nordic system. They are, on the other hand, starting to have it, because there are some challenges. So in the Nordic system, it works like this, that, okay, the wind power here in Denmark is decreasing. Then they see here, okay, the frequency is decreasing because we have a lack of production. Where is the cheapest resource? Then we have bids on that in the so-called regulating market, and then they find out that maybe, here we have some hydro here, and they could produce a bit more. Okay, can you compensate this Danish wind power with hydro here? And remember, this 2,000 kilometers. So it's, as I said, Allahabad down to northern Tamil Nadu, southern Tamil Nadu, which is around 2,000, not kilovolt, kilometer. Okay. And from what we are doing is that to check, and they are cooperating, and they are cooperating and saying that, okay, yes, it's possible from a grid point of view to replace this one with this one. Then we do it. And that is done within 15 minutes. This is, of course, efficient, but there are some challenges now of different kinds, so we are discussing to have some kind of, in some way, more automatic system. The challenge is that here we have the Danes, here we have the Swedes, here we have the Norwegian people, and they have different system operators, and they have to coordinate and accept what they are saying. So what I mean with this, with AGC, is a fantastic idea, of course, to handle this. But I think it's important that to make it rational, especially if you have much more solar and wind, it's perhaps better to compensate somewhere else, not as long as it's rational system point of view. And of course you should compensate. I must just check what I should concentrate on here. I have many slides. I just take 50% of this lecture so far, so I have it here. Okay, I will go into another part here. The question is then a bit what I've talked about, that you have, I mean, there are a lot of more controllability issues here. That is, let's say, the fundamental balancing. What I will go through now, and that is also what the tutorial will be about, and that is design of the future power system. Because then you come into all these kind of basic issues that you have to manage the peak, you have to manage the different situations, and then the question is how to consider all these kind of things. This, on the other hand, is a very complex tool. The question is, when you're talking about the future, which are the prices? Should it be cheap? Who should invest? Do we assume, for example, as I understand in India, the power sector is rather subsidized from the state? In the future, do we still want the power system to be subsidized by the state? Or do we think that the consumers in total should pay in reality what the power production costs? Do we accept which reliability do we have, and so on? So there are a lot of, let's say, discussions more than, I mean, then of course you have to have these technical issues about primary control, secondary control, which are the technical requirements. But when we decide the future power system, I mean, for example, this transmission, should we have local, there's a huge amount of things to discuss, and that is what I will go through. This is, we have a specific course in power generation, environmental markets. We have a specific course where we more or less think about when we have these challenges, but a lot of what I said today is in reality from that course. So I will go through this. The problems in Sweden, I don't think that here, I think you mainly see yourself as consumers, not as producers. Here I say that a challenge is in Sweden and currently in many other countries, and then I talk European countries, is that we have low power prices. Low power prices is of course an extremely big problem for a producer. I will show you, I had an equation earlier which was like this. Which is always valid. Then you can say, on the other hand, you have another thing, which is sum of cost, and then you have producers, grids, is equal to sum of income for producers, grids, is equal to sum of costs for consumers plus maybe state, or how you see it. It's absolute, I mean, this is as important. I mean, it's absolutely impossible for a production company if you have a coal plant or wind plant or a solar power plant, it's absolutely impossible to have this power plant if your costs are not covered. You have salaries, you have to buy things and so on. So of course the costs have to be covered. So the costs for the producers should be equal to the income for the producers. And then of course they probably have to make a profit also if it's a, and that's one of the issues. If you assume that these power companies should be private investors, then of course the income must be slightly higher than the cost, otherwise they don't want to invest. The question is, if you can also see that the cost is, if you borrow money from the bank, this is as fundamental as this one. It's absolutely impossible to run a company where you're making a loss every year. You must be subsidized. So the income, and then of course the question is how you handle this. And that is, let's say, the fundamental issue of the market. And when we're discussing the challenge in the future, and in the system, in the European system, I don't think any country in Europe is subsidizing the power sector. And this means that, and then what you have, the relation between the consumers and the cost, this is of course the same as the power price. This is equal to price of power. In the Nordic system, the challenge is very much that currently we have very low power prices. The power prices are much lower than it costs to produce any power. And this depends very much on that fossil fuel is very cheap. Fossil fuel and is very cheap, and the power price in the Nordic system is very much related to the cost of power in Germany. And in Germany they are using a huge amount of coal power, and coal power is very cheap in reality. And that is, let's say, one of the really big fundamental issues. I mean, we are trying to solve the greenhouse challenges here. This means that we should reduce the amount of use of coal, but coal is very cheap. How do you get rid of something that is very cheap? Who has the interest to do that? No one, if you don't put up some kind of political rules of doing it. Because if you allow coal, of course, coal is cheap. I mean, coal is cheaper than wind, if you don't have any cleaning or all these kind of things. So it depends on what are the rules here. So currently we have difficulties in reality to fund the existing power plants. They have the same problem in Germany. What they did in Germany, they built new gas plants, because natural gas plants is more environmentally friendly and better controllable than coal power. But on the other hand, they built these power plants, but then the coal price went so low, so it went extremely cheap to run the coal. So they keep on running the coal, and they just built a new, there are examples of 1,000 megawatt gas-fired plants that are not used because they are too expensive to run. And too expensive means that the power price is so low, so you don't get your operating costs covered. And I think this is one of the fundamental issues. I have discussed with, not with you, but with Nand and some other ones. But I think for India, what I think is that, as I understand, the power price is rather subsidized today. Someone said that it costs 6 rupees per kilowatt hour or something like this. 6 rupees, I think, per kilowatt hour. Was that right? I think. No, it's more. Pardon? 4.5. Okay. And then the question is what will happen with this? Because if you see it from India point of view, I think that in some way the question is where India will move. Because I think that you need investments in the power sector. You need to have cleaner coal and this kind of thing. That will need funding. The question is, will that funding come from the state? Which means that, and the state don't have a lot of money. Of course, they can print the money, but then you get inflation, so that's not very good. But of course, the question is, will they get it from the state, or will they sooner or later say that perhaps the one that want electricity need to pay for what the electricity costs, and then the price will go up. And then the question is, if you try in India, which I think is a very interesting scenario, if you try to increase the price in India for the final consumers, then probably at some level it will be profitable for these consumers to build their own solar power instead, because it's cheaper. And on the other hand, because this is one of the fundamental problems, that since you are keeping down the prices for consumers, they don't have any interest in solving the problems, which is probably the most rational way in India to start with using solar power. I mean, at least in the coming 5 years, if you see the price trend. So a problem in India is that you are subsidizing the price, which means that you are taking away the interest to use solar power. And then you have to subsidize solar power to get it down, and so on. Or if the power producers may do it. So I think that this policy issue is very, very important when you are discussing and how to arrange the system. But I think this fundamental issue, that in some way, remember that it's absolutely impossible for a power plant owner. I mean, you can have requirements on whatever they should do, but I mean, it's impossible. They will not use their power plants if they are not covering their costs. The question is, how are they covering their costs? Are they covering their cost either by, and they, for example, if it's a state-owned company, also the power producers can be subsidized. But then, of course, who's paying the tax? I mean, then the state has to be subsidized instead. Or subsidized, the state is subsidized. But I mean, the state then have to get the money in another way. So whatever you have the costs here. Should they be paid by the consumers or by the taxpayers? The benefit of having it through the taxpayers is, of course, that you can select if it's the rich ones or it's the... But on the other hand, the rich ones are very often very smart in not paying so much taxes, to be honest, and that's what we see all over the world. So, I mean, the challenge is always, I mean, how to handle this. This is a challenge in every country, of course, how to handle this thing. But the fundamental issue is that, and especially now when you have this cheap that is really increasing, then of course, cheap solar power, then of course, then you see another trend nowadays, that if you just have the prices which are reflecting the costs. For example, in Sweden, one of the reasons why I have solar power is that the tax is so high. I have tax on my electricity. So the cost of electricity is like this, but what I pay for electricity is like this. And then, of course, solar power for myself is then, of course, more attractive since I have such a high tax. As I understand, in India, it's more to say that the cost is like this, but you pay like this. And then, of course, it's more difficult to get profitability in your own solar power. But I think that I have to, and then the question is, of course, state can go in everywhere and say that we subsidize the electricity, and then we also subsidize the solar power. So you will build solar power, which is good from the national economic point, but not for you, so we have to subsidize them. So then they subsidize the solar power and subsidize the electricity. So it starts to be a bit complicated, but I mean, there are a lot of political issues here, of course, because, I mean, you have a huge amount of poor people and they cannot pay more for the electricity, and not everyone can install solar power. So, but this is certainly a challenge here. So, you can call it that the aim of the future power system. This is just a general, I mean, this is this general aim everywhere. You want to have competitive prices. You want to have, of course, low. The question is prices. What do you mean with competitive prices? Perhaps we should say low costs instead, or competitive prices. Because the prices you can manipulate if you just have the state is going to take taxes or take subsidies or so on. But when I say prices, I mean in some way that is the interaction between these ones and these ones. For example, competitive prices, that is what politicians say in Sweden. We must have good prices. And then the consumers say, yes, yes, very good. This means low prices. And the producers say, yes, yes, competitive prices. We must be competitive. They must be high. So the politicians always love to say that we love competitive prices. And then the heavy industry in Sweden, for example, the steel manufacturers that use a lot of electricity, or the cement factories or paper industry, they are using a lot of electricity. They say competitive prices. Yes, of course we should have competitive prices. They should be on a level so that we can compete with China or whatever. So competitive prices everyone loves, but it means different things depending on if you are a consumer or a producer. Then should be sustainable, which it is not, and of course we also want our kids to survive. I think that sometimes if you see a kid in the street, 4 years old, okay, and then just remember this person will live into the year 2100, which seems to be very far away, but it's not that far away. And then the question is sustainability. It's not only for the coming 5 years. It's slightly longer. And then we have reliability, of course. Reliable it should be. And then, of course, we also need efficient operation, which means in reality efficient operation. So you are using exactly, I talked to this about AGC, that the question is how to operate the system in a smart way. Efficient planning, you should have a lot of, so you build the right line in the right time and so on. So this is, of course, a big challenge to get all these kind of things to really work. Okay, now I have already said everything. Competitive prices, what is that? Competitive for consumers, not too high. Competitive for producers, not too low. But here I think that because here's a difference compared to India, because in Sweden, the price, that is a price. And the producers see the price, and the consumers see this price. While in India, it seems like, yes, there is a market, the producers see this price, but the consumer sees a completely different price, which is subsidized. And then the question is, how is this, let's say, the difference, because this means that it's a retail. And then they're selling to a consumer for a much lower price, and this means that they have to be subsidized in some way. And how is that handled? Prices are set on a competitive market, and that is what we have in Europe very much, and or regulation, and that's what you see here. And then I said that state might be involved concerning subsidies and or taxes, and that is, we don't have so much subsidies, we have more taxes in Sweden. So the power sector is a very big income for the state. And then, of course, subsidies is what you have. On the other hand, we have subsidies. It's interesting. We have subsidies for wind power, but the subsidies are in reality paid by the consumers, but not the industrial consumers. I think it's a bit of difference in what I see very often, that in Sweden, if you see, as I understand, if we take India or if we take United States, the final consumers, they really want to have low prices. In Sweden, we have very strong unions, and we are a strong export nation, and this means that the unions are very much supporting the employed people that are working in the industries. So in Sweden, the policy is very much to keep down the electricity prices for the industry. For the industry, because the industry have competition from abroad. The final consumers, that's not so important. So in Sweden, it's very much that the final consumers, they are paying for this green power, so-called certificates that we have in Sweden, but the industry doesn't have to pay for that. So in Sweden, it's not the single person that is important from the political point of view to keep down the prices for consumers, while in India, this is extremely important. I also heard about in the United States, it's very much political pressure to keep down the final consumer prices. While in Sweden, it's more that we are keeping down the prices for the industry. And the final consumer can pay tax. That's not the problem. I think I stopped there, because now it's 10 o'clock. Okay. Thank you. So